Hello, welcome back to the lecture series on microeconomics. We have been theorizing the production behavior of a farm. We have seen the concepts of neoclassical production function, isoquants and various types of elasticities. These are basically alternative representations of the technology which is used by the farm. Now, with these concepts defined, let us look at the problem a farm faces. We are going to now discuss the optimization problems of a farm, and they are of three types. We are going to discuss them one by one. So, the first problem of a farm can be described as output maximization subject to resource constraints. The second problem can be described as cost minimization subject to output constraint. And third and the final problem is basically the problem of profit maximization. We are going to assume the case of a two variable input production function as usual. So, we are going to assume that we have a two variable input production function written in general form, but the analysis we are going to do now can be generalized in any time. So, let us now look at the first problem, which talks about finding the maximum level of output that can be produced given a budget of a farm. So, let us first look at the budget constraint of a farm. Here you will find that there is surprising similarity with what we have already done under the heading of theory of consumer behavior. In the case of consumer behavior, there was a consumer, he or she was trying to maximize his or her utility subject to a budget constraint. Here also we are going to follow the similar procedure to find a farm's equilibrium. So, we are going to work with the problem number 1, which is basically output maximization. Now, in this problem, let us assume certain things. So, we can assume that the farm has C naught amount of money, that is basically the resource to the farm to start with, and that is a given parameter in this optimization problem. And as there are two variable inputs, we have to assume two input prices. So, this is price or unit price of input 1, it implies x1, and W2 is price of input 2, it implies x2. So, now we are going to write something which you have already seen. So, in the case of consumer, we wrote the budget constraint. Here also, if the farm spends the entire amount of money C naught on two inputs, then we can write this particular equation, right. And what does this give? This represents different combinations of x1 and x2, it implies input levels which will perfectly utilize the resource. It means that the money, entire amount of money will be spent on these various combinations of inputs, and as the cost level, as the resource level is given and the resource is basically is cost here, this is known as ISO cost line, right. This is exactly similar to the concept of budget constraint in the case of consumer behavior. So, now let us look at a illustration how we can so we are going to measure our variable inputs x1 and x2 as usual, and now let us have a look at the ISO cost line equation. So, if the entire money or the resources are to be spent on one particular input, say x1, then how much units or how many units maximum one can purchase of input 1, that is given by C naught divided by W1, right. So, similarly, if the firm wants to spend the entire amount of money only on input 2, then it can purchase C naught over W1 units of W2 units of input 2. Now, of course, we can join these two extreme points, and as we assume that these input prices are also given, means they are constant. So, we get a straight line, and this is basically the diagrammatic representation of the ISO cost line. So, we can denote a particular ISO cost level as C naught in this case. So, note that if I now increase the monetary resources to the firm to a level C1, this curve will move up parallelly. Right. So, let us denote this by C1. So, note that we can generate series of ISO cost lines actually, but for this particular problem we will not require two different cost levels because we are talking about a particular cost level only. So, as of now let me erase the second ISO cost line for the higher amount of money. Now, what would be the slope of this ISO cost line? So, for slope we can let me note these points by A and B, right, and of course O is my origin. So, the slope will be in this case minus, because it is downward sloping, OA over OB, right, and that will be nothing but minus. Now, note that here I have used the geometric technique to find the slope, but of course you can take total differentiation as we have done earlier to find this slope value. So, what next? We have already seen in the case of a constraint optimization problem, we have to adopt the technique called Lagrangian method. So, here also we have an objective function and a constraint, and we can frame the Lagrange expression. Let us have a look at that problem. So, here what is the firm's problem? Firm wants to maximize output, which is represented by my 2 input production function, and the firm faces a constraint, budget constraint you can say, which basically is given by W1 x1 times W2 x2. The total expenditure on inputs shall be equal to the given level of resources for full. So, basically we are assuming full utilization of resources, right. So, here this is the optimization problem, and the decision variables of course will be x1 and x2 because others are parameters in this model. Now, we need to set up the Lagrange. So, for Lagrange we can write right. So, where lambda is basically my Lagrange multiplier. So, now what do I need to do? We all know that take partial derivatives with respect to the decision variables, hence we get so say this is my equation number 1, then of course the second one will follow. So, this f1 and f2 are basically the first partial derivatives with respect to the input levels, and lastly we have to take derivative with respect to the Lagrange multiplier as well to enforce this equality of budget constraint. Right. Now, what do we get from all this? So, you can probably anticipate the result as we have derived this kind of Lagrange before. Right. So, now let us see how can we interpret this particular expression as denoted by star. So, this is basically the crux of my first order condition. So, these are my first order conditions. So, now let us try to find out an explanation for the expression given by asterisk. So, what do we have if we take this expression 1 over W1 and 1 over W2? It simply gives the number of units of a particular input that can be purchased through 1 unit of money, say $1 or 1 rupee. So, when we have the number of units of a particular input, and if we multiply the marginal productivity of that input, then basically we get the increase in output, right. So, that way the first element f1 over w1 shall represent the increase in output if we spend 1 unit of money entirely on input 1 or x1. So, similar explanation is valid for the second component as well, which is f2 over w2. So, the lambda basically gives the marginal productivity of money. So, why it is marginal productivity of money? It shows if we spend 1 unit of money, say $1 or 1 rupee, then how many units of additional output we can produce. So, lambda has this interpretation of marginal productivity of 1 unit of money. and that can be given by dollar or rupee, whatever. So, mathematically we have derived the solution to optimization problem for Firm's first type of problem. Now, let us have a graphical way to find the solution to the same problem. So, different levels of output is given by different iso quant or iso product level curves, and a higher level of iso quant gives a higher level of output or shows a higher level of output, right. So, in this case basically if we superimpose the iso quant map, then the firm will try to be on the highest possible iso product curve or iso quant. So, that will happen if firm finds a point like this represented by say point P, where the iso quant represented by Q star level of output is tangent to the iso cost line, which is represented by C naught. So, now we can see that the firm finds optimal levels of input x1 star and x2 star such that highest level of output. So, this is basically highest possible output, right. So, what happens at that tangency point, which is the equilibrium? So, at equilibrium, which is determined by the Lagrangian as well, what happens? The slope, absolute value of the slope of the iso cost line, which is given by W1 over W2, shall be equal to the absolute value of the slope of iso quant, which is given by MRTS, which is basically the ratio of the marginal products, right. So, we basically get back the same expression from graph, we get the same condition from the graphical analysis as we have seen in the case of Lagrange, which is given by this single asterisk expression. Now, we have obtained the first order conditions for the optimization problem of the firm. Shall we check for the second order condition? Yes, you can follow the Hessian technique that we have seen earlier to check for the to check whether the second order condition is satisfied or not, but as we have presumed nicely behaved isoquant means convex to origin and downward sloping, we are ruling out abnormal cases of isoquant. So, let us not get into the second order conditions, we assume that they are satisfied. Now, let us move to the second problem of the firm, which is basically finding the least cost possible way to produce a particular output level. So, the second problem can be summarized as cost combination So, here straight away we start with the Firm's objective function in a mathematical manner. So, basically here the problem is of a minimization type. Here the firm wants to minimize cost of producing a particular level of output. So, that constraint is represented assuming level of output that is prefixed, say Q naught, right. So, here what are my decision variables? Of course, my input variables, right. So, here also we formulate Lagrangian as well, and we write this time we assume a new Lagrange parameter mu. Soon we will see that that is different from lambda in the previous case, and hence we are differentiating with symbols here. Right. So, I am not showing you all these partial derivatives and all. I assume that you are confident by this time to take derivatives yourself and finding the first order conditions. I am giving you the crux of the first order condition. So, you can find these first order conditions to get this result, which is given by this equality or this expression, right. Now, the task at hand is to find an interpretation of this expression, right, which is given by 3 asterisks. To find out the interpretation for 1 over f1 and 1 over f2 terms, let us have a look at the marginal product diagram, that will help us. So, I take any particular input, say x here, I am not writing subscripts 1 and 2 to make it general, and then let us write f prime. So, that is basically the marginal product, which is basically the case f1 and f2 if we have specific inputs with respect to which we have to take derivative. Okay. So, now we know that in conventional cases, in standard cases, marginal product is a downward sloping function. It can be concave to origin, convex to origin, straight line to origin, we do not care as of now. We will just say that what does it give actually. So, we fix a particular level of x and then we go up to the marginal product curve, and that basically represents the level of increment in output, which is basically marginal productivity at this particular level of input use, say x prime. So, that is MP prime, right. Okay. So, now we can also look at the reverse side of it. So, suppose I now say that I want to see increment of 1 unit of output. So, I can fix the value 1 here along this axis, and now I can always go back to my marginal product curve and figure out the number, the unit of x which will give me that value of marginal product, which is basically 1, right. So, we can say that that is basically an input level, say x tilde. So, this inverse of the marginal product function, which is given by 1 over f1 and 1 over f2, can be represented or can be explained as the number of units of a particular input required to produce 1 unit of output only from that very input, and keeping the other input fixed. So, what is the interpretation of W1 divided by F1? So, that is basically the cost if the firm decides to produce 1 extra unit of output through employing only the variable input x1. Similar explanation holds for the input 2 as well, right. So, now let us look at the interpretation of the Lagrange multiplier in this case. So, certainly what we observe here is basically an increase in the cost on farm's side to produce one extra unit of output. This is named as marginal cost of production. So, mathematically we can write, note that there is this relation mu is basically 1 over lambda, or alternatively I can also write lambda is basically mu inverse. So, there is a relationship between two Lagrange multipliers. Now, let us look at a graphical solution to Firm's cost minimization problem. So, here we have to start with a particular level of isoquant displaying output level Q naught, and we have to achieve the minimum possible cost for which the isocost line will become tangential to the isoquant, because that is required by the Lagrangian method solution. So, here what we are going to do, we are going to start with one isoquant displaying the output level Q naught, and now we are looking for a series of isocost lines in this input plane, one given by this, then there can be one more. These are all parallel translations of the same isocost line having different resource values or cost levels, but with the same input price ratio. So, our target is to go down, right. Now, how far you can go down? You can find an isocost line such that it becomes tangential to the isoproduct curve or the isoquant at a particular point, say denoted by point P, and that is the least cost at which you can produce, because if you go down further, say to this level, then you cannot produce that output level Q naught. Hence, I erase this infeasible isocost line. So, what do we get? We basically get the least cost input bundle, which is represented by the equilibrium point P. So, we get x1 star units and x2 star units of inputs that will be able to produce Q naught level of output in the least cost manner. So, now let us look at the first order Firm's equilibrium from the graphical analysis and try to match the condition with the first order condition we have derived from the Lagrangian exercise. Here what do we see at equilibrium? So, at point P, basically we observe the input price ratio, which is basically the absolute value of the slope of the isocost line, which is given by W1 over W2, shall be equal, which is given by F1 over F2, right. That is exactly equal if you see the first order condition right here that we have derived earlier. We will continue this discussion on optimization behavior of Firm in the next lecture.